Hello YouTube. In my last video I introduced the Hamiltonian formulation of classical mechanics, which is nothing more than a coordinate change from q dot to the canonically conjugate momenta p. From now on we will assume that we can solve for q dot in terms of p from the definition of p, which is dl dq dot. This means the Jacobian of the transformation, which is the Hessian of the Lagrangian, is invertible. These beautiful symmetric Hamiltonian equations imply that a general function a of q and p will evolve according to this Poisson bracket. The Hamiltonian equations themselves are a special case. The Poisson bracket of position with its canonically conjugate momentum equals 1. All other pairs of phase space coordinates have vanishing Poisson bracket. We can represent this using the Kronecker delta symbol, which is defined as 1 for matching indices and 0 otherwise. And we call these canonical commutation relations, CCR. Suppose we define two new variables, big Q and big P, where the I index runs from 1 to n, forming a coordinate transformation representing the original phase space coordinates with these new variables. The transformation is canonical if the new variables also satisfy the canonical commutation relations. In matrix form, we're saying that the Poisson bracket between Q1 and P1 is 1, and if I add a Q2 row to the matrix, my answer becomes a column matrix with two elements, the Poisson bracket of Q1 with P1 and Q2 with P1. Alternatively, I can expand this matrix with extra columns for different momenta, and my answer becomes a row matrix containing Poisson brackets of Q1 with, let's say, P1, P2, P3, and so on. So let's say I expand out both of these matrices to contain all the Qs and all the Ps. The answer is then a 2n by 2n matrix of Poisson brackets of Qs with Ps, Qs with Qs, Ps with Qs, and Ps with Ps. If these big Qs and Ps are truly canonical, then QQ and PP brackets have to vanish, and QP brackets and P1 brackets have to equal 1 and negative 1 respectively whenever the indices match, and 0 elsewhere. But this is just the symplectic matrix. And these matrices have derivatives of each new variable with each old variable. Whenever you have a coordinate transformation and you can form a matrix of the new variables differentiated with respect to old variables with the rows and columns arranged in this way, in this organized way, that's called the Jacobian matrix. To say that the transformation is canonical is to say that if you sandwich the symplectic matrix between the Jacobian and its transpose, you get the symplectic matrix back. Transposing a matrix doesn't change its determinant. So on the right we have a determinant of 1, and on the left we have det j times 1 times det j. Therefore det j is just 1, or negative 1, but we're not going to look at that case. Okay, but if the Jacobian determinant is the scale factor going from one coordinate system to another. So suppose you have a set of points that cover a small region of the original coordinate space. When you perform this coordinate transformation, those points mark out a region in the new space, and the determinant of the Jacobian matrix is the ratio of the new volume to the original volume. That proves something called Liouville's theorem, which states that canonical transformations, these guys, always preserve phase space volume. Suppose A and B depend on our new variables. If we want their Poisson bracket, the multivariable chain rule tells us how to differentiate with respect to little q and p. But if the new variables are canonical, then this middle product here is just a symplectic matrix. This means canonical transformations leave Poisson brackets invariant. We can just differentiate with respect to our new variables and treat q and p as our new system coordinates, because our old variables are no more special than these new ones. The time evolution of our new q's and p's follows exactly the same rules as our old variables. The time derivative of q, which is this expression in our old variables, simply becomes dh dp in our new variables, and likewise p evolves as negative dh dq. So it's all well and good that we have a definition of a canonical transform, but how do we go about finding them? First, I'll give you one construction that guarantees the brackets are canonical, and then I'll talk about a different method of producing canonical transforms. Suppose this function f depends on both little and big Q, and we define little and big P like so. I assert that if we rearrange big Q and P to depend on little q and P, their brackets will be canonical. To check this though, we need to know how Q changes with little q while holding P constant, while holding little p constant. And also how it changes with little p holding little q constant. And likewise for P, for big P. We have awkwardly defined big and little p in terms of big and little q, so we need to rearrange the change in q and the change in p so that we can get the derivatives we need. So let's suppose we move this term over to the left and invert this matrix. So let's call the matrices A, B, C, and D. So the change in q, this column vector, is the negative inverse D times C times this column vector, the changes in little q, plus inverse D times the changes in little p. Meanwhile, big P depends on little q, both directly and through its dependency on big Q, giving us A minus B inverse D C. And so we read off the derivatives we need. What is the Poisson bracket between one big Q and another big Q? Let's substitute matrices into the formula. Okay. Now to see that this thing is actually zero, you have to remember that all these relationships came from a single function. So the equality of mixed partials guarantees that B and C are symmetric matrices, while A and D are negative transposes of each other. So let's check the PP brackets next. Substitute the matrices, and remember that to transpose a product means to transpose each factor and reverse the order of multiplication. So the transpose of D is just A, and multiplying its inverse gives the identity. So both these terms reduce to B, which is the same as B transpose. And so we see again that these brackets vanish. Finally, let's calculate the QP brackets. Transpose of A times inverse D gives the identity. Meanwhile, this term cancels with this other term. To recapitulate, we began with one function of big and little q. We defined big and little p as derivatives of our generating function. These matrix elements are just mixed partials of f, which guarantees that B and C are symmetric while A and D are negative transposes of one another. So are these Poisson brackets canonical? Well, to check, we need to differentiate big and P and big Q with respect to little q and P, holding the small variables, the other small variables, constant. When we rearrange these matrices to get the required derivatives, we find we can use them to find each Poisson bracket, and we see that yes indeed our construction defines a canonical transformation for any generating function f. Now is the converse true? Given an invertible transformation between two sets of coordinates, can we produce a generating function f that does the trick? Well, that depends. If we can rearrange these relations so that each big P is a function of big and little q's, then if that's the case, we can substitute and get little p in terms of big and little q. So we have big and little p in terms of big and little q, and our generating function is the antiderivative of any of these in terms of the respective q. We can prove that you get the same answer, the correct answer, by running our logic backwards. Let's define the A, B, C, and D matrices. We know that the QQ brackets all vanish, thus confirming that C is symmetric. We know that the matrix of QP brackets equals the identity, confirming that transpose A equals negative D. And finally, the PP brackets vanish, confirming that B is symmetrical too. These three facts guarantee the equality of mixed partials, and that confirms that all the matrices are derivatives of the same function, f, to within a constant. So you can pick a momentum, any momentum, and integrate it, and you will get the generating function. Okay. Now, I started with a big if. Given an invertible transformation, Can you always rearrange it like so? Well, let's start with big P1 and substitute the equation to remove all instances of little p. Now, in theory, we can express big P in terms of big and little q, and possibly some of the big P other than P1. Now, use this equation to replace all instances of big P1 so that it appears nowhere else. It appears nowhere else now. Next, we move on to big P2. We substitute to remove the little p's from its equation and solve for big P2 in terms of big and little q's, and possibly some big p's, except for P1 or P2. And this can substitute for all other instances of P2, so that P2 now appears nowhere else. We can theoretically continue this equation for we can theoretically continue like this unless this equation for big P is degenerate. If the left and right hand side both say big P, then this equation tells us nothing about big P. And that could happen if the transformation between big and little p involve each other but nothing else. This is where the generating function idea breaks down, and we could allow ourselves the liberty of swapping q for p and p for negative q. So if we change the problem slightly, we can once again codify the canonical transformation into a single generating function, provided we remember to swap the coordinates back when we write the transformation out. So with that extra liberty, we can indeed represent every possible canonical transformation using a generating function. Canonical transformations are a dime a dozen. This construction works for literally any smooth function f of the big and little q's. This coordinate transformation has nothing to do with the underlying system. It doesn't matter whether the Hamiltonian represents a pendulum or a spring or a car or a solar system. It really doesn't matter. The canonical transformation is just a relabeling of one or more variables. You substitute everywhere to express the evolution of the system using these new variables. The Hamiltonian becomes a new function in terms of the new variables, while representing the same system and the same physical quantity. If we have a generating function that depends on little q and big P, we can alternatively define big Q and little p as such, and we actually have a very similar argument to the one I gave before that confirms that this transformation is also canonical, and that's called a type 2 generating function, while this setup here is called a type 3 generating function, and here we have a type 4 generating function. So in fact, if we have more than one canonical pair, we can actually mix and match. For example, let's say f depends on big and little q1, and also depends on little p2 and big q2. So it's type 1 for the first canonical pair and type 3 for the second canonical pair. Alternatively, we can construct canonical transformations from a series of infinitesimal transforms. Okay, suppose this generating function is type 2 for all the conjugate pairs, and g is some function over phase space. Suppose k is some small number. We define big Q and little p as derivatives of f2 in the usual way, but because k is small, the transformation is close to the identity transformation where big and small coordinates are approximately equal. You can see if k was 0, then they would be equal. Okay, and what that means is we can fudge it a little bit so that we write little p in the place of big P. So how much error do we introduce if we do this? Well, as you can see, these terms cancel, as do these and these. So our derivation from the canonical brackets, our deviation from the canonical brackets is second order in k, whereas the change in q's and p's is a first order quantity. If k is small enough, we can throw away these second order quantities and see once again we have a canonical transformation. We can substitute everywhere to get rid of little q's and p's, and all functions preserve their value if you substitute these for little q's and p's. There may be some special functions where the old q's and p's give the same value regardless. We say that the function is symmetric in this generator if the change in f is 0. In all other cases, if we choose to keep the original q and p, f will change by this amount k times the Poisson bracket. In any case, we can pick a very small value of k. We perform this operation many times. With each iteration, the canonical Poisson brackets change by some quantity proportional to k squared, while each point on phase space moves by some distance proportional to k, and that discrepancy enables a limit where k tends towards 0, and we perform an infinite number of steps. And I rename this k as delta tau, and parameterize the motion of one point in space, big Q and P, as a function of tau. These equations begin with big P and Q equal to some point in phase space, little q and p, and the differential equations that describe movement are the continuous analog of these rules. Now, you can pick any fixed value of tau, and big Q and P is some point of phase space that is a function of little q and p. By induction, we know that they are canonical. Now, is it just me, or do these equations look strangely similar? So if we wanted to, we could have picked G equal to the Hamiltonian. So the moral of the story is that time evolution is a canonical transformation. So in other words, Liouville's theorem tells us that if we begin with a certain volume in phase space, suppose it reflects your uncertainty about the system state, you can evolve the system to a later time, and you will, at best, end up with the same amount of uncertainty that you began with. That implies conservation of phase space, and therefore conservation of Shannon entropy. So we're going to talk about that later in a future video series when I discuss thermal physics and talk about ergodic systems. Okay, so we can directly relate the divergence of the Hamiltonian field and see that it equals to 0. So this is divergenceless, or incompressible, or solenoidal, three words that mean the same thing about a vector field. So far I've discussed canonical transformations in the Hamiltonian picture without any reference to explicit time dependence. In my next video we will see what happens in the non-autonomous case. So I'll see you there.